Welcome back. I think I'm being watched. Today we're going to complete Chapter 3. Here are today's topics, and one last time, the chapter objectives. Processes are independent or cooperating. Independent processes don't communicate with each other, and in fact it's desirable that they be isolated from each other. Cooperating processes need some sort of a communication mechanism, and you can see from the bulleted list why we would design a software system with cooperating processes. And we'll be looking at two process communication models: shared memory and message passing. Here's an abstract diagram of the two communication models, message passing on the left, obviously. For our concrete example, consider a web browser communicating with a web server over the internet and the TCP IP protocols. So the web browser sends a message to the web server saying, please fetch such and such web page for me. And the server responds back with a message containing the HTML of that web page. For a specific example that should be easy to understand of shared memory, consider threads, two threads operating within a process. They each have their own local storage, but they both share, right, have equal access to any global variables that are defined within the program. Once again, we're focusing on cooperating processes here that depend upon each other and can influence or affect each other. Producer-consumer is the classic problem in this area. We have a producer process producing messages, a consumer process consuming messages, with a buffer in between. So the producer produces into the buffer, the consumer consumes from the buffer. And if the buffer is of infinite size, then the two processes don't have to coordinate their action at all. If the buffer is of bounded size, then if the producer is producing much more quickly than the consumer consumes, eventually the producer is going to have to wait for a buffer to empty up so that it can produce its next message. The limiting case here is no buffer at all, in which case there's a strict interplay between the producer and the consumer. So here's one potential data structure for the buffer itself. The next two slides will show the pseudocode for the producer and the consumer. So note that buffer in and out are shared global variables. So here we see the solution for the producer. In is an index into the buffer array of the next empty buffer, the next buffer to be filled. The condition in the while loop there is meant to distinguish between the buffer array being completely full and the buffer array being completely empty. Obviously, if we got confused about those two situations, the solution would not be correct. And given that the buffer is implemented as an array, we have to perform modulo operations, which are the percent operators there to wrap the indices from the end of the buffer array back to the beginning. Here's the consumer code. Out points is the index of the next element of the buffer array from which a message will be consumed. And you can see in the while condition that if in is equal to out, that's the logical condition for buffer empty, in which case the consumer has to wait for a buffer element to be filled. I want to focus on this third bullet here just for a moment. When processes share memory, access has to be synchronized. Consider the kind of abstract following situation. Two independent processes read a shared variable at about the same time into local variables, private storage, update the variable locally and then write it back to shared memory, the first written value will be overwritten by the second written value, and the final value of that shared piece of data will not reflect both updates. But that's a problem for process synchronization to solve. Here are some of the parameters of the message passing communication paradigm. I don't see anything here that I particularly need to point out. Okay, so I will point out that there's a natural synchronization message here. Obviously, a receiving process can't do a receive until the sending process does a send. All right, so here we see some implementation issues. How is the communication link set up? How do the processes find each other? Once we have a communication link set up, can more than one process execute a send on that link? Can more than one process execute a receive on that link? What do two receives look like? Can two processes receive the same message or not? How many links can each process set up? How much storage is in a link? What do the messages that are sent into the link look like? Are they fixed block sizes or variable? And finally, is the link itself, let's say we have two processes using the link. Can they send information back and forth in both directions? That's bidirectional communication. If messages can only be sent from one process A to process B, we call that link a unidirectional link. Here we see that the message link can be implemented on top of a shared memory API. It can be implemented at the hardware level, or it can be implemented across a network using the networking API. The link might be direct here means that messages are directed to a specific process. Indirect means they're sort of just dropped off in a mailbox or a drop box. Abstractly speaking, synchronous message passing is, for example, a send operation with synchronous will block until the receive occurs, and asynchronous message passing sends don't result in blocking. Receives could be implemented on the asynchronous model in a way by allowing for a receiving process to peak to see if there's a message available so that it doesn't block, and then finally whether buffering is provided automatically or has to explicitly be requested. Here we see the direct communication model where our processes name, the sender names the receiver names the sender. There's no setup involved. The link is established automatically. One process just does the send to the other process. It's implied that a link has exactly one sender and exactly one receiver. There is a pair, in essence, or a link for every pair of processes. And as stated at the end there, the link is usually unidirectional. I'm sorry, the link is usually bidirectional. I've read that bullet a little too quickly. In indirect communication, a sending process doesn't name a receiving process, nor does a receiving process name a sending process. The communication is via mailboxes, or in the case of networking, ports. So for instance, to go back to the web browser, web server analogy, a web browser sends a message to port 80 on a server, and the web server on that server, that computing system is listening on port 80. And then many web browsers can use that port 80 to communicate with the web server, looking down at sub-bullet 3 of the second bullet. The link may be associated with many processes. And that's about it for that page. So as you can see here in the indirect communication model, there's some setup involved. Going back to the web browser, web server example, when the web server starts up, it has to open port 80 so that it can begin receiving messages on that port. And when it shuts down, it will release port 80. And you can see what the send and receive API calls look like. There is the mailbox or port number. So here we see some solutions to the situation of multiple processes performing receive operations on a mailbox. Going back to the web server example, a possible architecture for a web server implemented as multiple processes to handle a large number of incoming requests would be to designate one of the processes as performing the receives on the port and then distributing them uniformly among the remaining processes, which will actually handle the request and communicate the results back to a web browser process. Here we see blocking and non-blocking semantics. Blocking is considered synchronous. So if the sender sends before the receiver receives, the sender will be blocked until the receive happens. Also, alternatively, if the receive is performed first, the receiver is blocked until the sender sends. Non-blocking is considered asynchronous, so there's no synchronization between the sender and the receiver. So the sender sends and immediately continues regardless of whether a receive is being performed. And with a non-blocking receive, if there's a message, the receiver gets the message, otherwise it gets the null or empty message. And the point in time and in the code in which blocking semantics are applied is, as you can see, called a rendezvous. So here you can see that the message passing solution to ProducerConsumer is much simpler than the shared memory solution to ProducerConsumer. The producer sends, the consumer receives. Here you can see the three possibilities for link buffering. A zero capacity or no buffer forces senders and receivers to rendezvous. They have to synchronize. A bounded capacity buffer allows a certain amount of asynchronous activity. If the buffer is full, a send will block. If the buffer is empty, a receive will block. And then finally, the limiting case is an buffer of infinite length. I'm going to skip over this slide and instead walk you through the code on the next two slides. Here's a producer example of shared memory between processes. So this is the size of the shared memory, 4K bytes, the name of the shared memory object, and two messages that the producer will produce into the shared memory. We have an int file descriptor for the shared memory object. The semantics of these shared memory operations at a high level are akin to those of a file system, and a pointer. So here is the, you can see the API call to the shared memory open. The parameters look a lot like those of opening a file. If the shared memory object does not exist, the open call creates it. If the shared memory object does exist, this simply opens it, and it returns the file descriptor. This establishes the size of the shared memory object, and this maps the shared object into the process's address space. So in a sense, you can think of this, since the messages being passed are strings, as this is dynamically creating an array of bytes. And since we're writing string data, you can think of it as a character array. So here is where the two messages are placed into the buffer. This takes the first message and places it into the beginning of the buffer. This extends the pointer to just past the message, and then this places the second message into the shared memory object. Do note that the way this is implemented, the two messages, hello and world, will actually be concatenated together into a single message. So here's the consumer process code, similar operations going on. Open the shared memory object, map the shared memory object into the process's address space. This will read the shared message, printing it on the terminal, and then finally destroy the shared memory object. I'm going to skip this. I'll also skip this. I'll skip this as well. We'll take a brief look here at sockets, RPC, and pipes. So in TCP, which is a bidirectional network communication protocol, a TCP connection is defined by two sockets. Right, as you can see here, a socket is defined as an ordered pair, an IP address, and a port. So a TCP connection is an ordered four tuple, and that ordered four tuple uniquely identifies a communication link between two processes on potentially different systems. So here's a figure illustrating the concept. On the left, a web browser is using port 1625 to communicate with a web server on the right that is listening on port 80. Java has a fairly clean socket API built on top of other I/O APIs. So in this server example, here we see this server attempting to open a server socket, a listen connection on port 6013. If that's successful, it goes into a server loop here where it waits on a connection, an incoming connection. It's an output stream which allows it to print the incoming message, then close the client connection. And after closing the client connection, it will return to the top of the while loop and begin listening for the next incoming client connection. Remote procedure calls, or RPC, consider the following situation: a process running on one system, process A, and process B running on another system, and we want, process A wants to execute a function within process B. How do we make that happen? Well, process A can group the parameters to the function in your message, send it across to the other system. Process B unpack those parameters, execute the function, and then wrap up the return value into a message and pass that back to process A. However, given that these are arbitrary processes, process B might not be listening on a specific port. So how does process A get in contact with process B? That's an important question, and we'll take a look at that question coming up. Here are a few details that would have to be considered. We'll gloss over these. What I want to focus upon here is the problem that I raised a moment ago. How does process A determine what port to send its parameters to? Well, it turns out that there's a matchmaker, as it's called here, process listening on a well-known port that can be queried by process A to determine what port to send to in order to communicate with process B. So when process B starts up, it registers its services with this matchmaker, which then can direct incoming requests to the appropriate, not exactly direct incoming requests. It can simply reply to remote processes with the port number they should use for a specific service. So what's required in this instance is that all the server processes use unique names for their services, right? Otherwise, there are going to be collisions in that namespace. So in a Linux shell, the vertical line character is used to indicate a pipe. So when you use that on a command line, let's say A pipe B, A's output is connected to B's input. So whereas A would ordinarily send its standard out to the terminal, that standard out is connected to the standard in of B, which ordinarily would have been the keyboard. And as mentioned, the pipe is created within a single process. Here that would be the shell process, which then forks two child processes, A and B. And due to the semantics of fork, all the pipe resources shared. So both child processes have access to it. They would then have to disconnect standard in on process B and connect it to the pipe, and process A would have to disconnect standard out and reconnect it to the pipe. In Linux, when you create a pipe, you receive back two file descriptors, one for reading and one for writing. So in a sense, you can think of a pipe as being a file with, in essence, a large amount of storage, and you are simultaneous. One process is writing into the file while the second process is reading from the file. In this case, by file, I mean pipe. I'll skip this slide, and that completes chapter 3. Gotcha.